let us now come to forward problems versus inverse problems. Okay, so this is the first introduction I am going to give, apart from the brief introductory video you would have seen on what inverse problems are, and it's best to see them in the context of problems that you are already familiar with. So the problems that you are already familiar with are what are known as direct or forward problems. Okay, so any textbook problem that you would have typically done in science and engineering are direct problems, but as we will see shortly, real problems in science and engineering are usually inverse problems. As you will see, I will give you a diverse set of examples. These set of examples are true not only in science, engineering, but also true in general in many things in life. Okay, so the most interesting problems both in life and in science and in engineering turn out to be inverse problems, but let's first look at direct problems. So what is a direct problem? A direct problem is a straightforward problem which says given the cause, find the effect. Okay, so for example, if I take a problem in Newtonian mechanics, I start with some ball at a particular place and I tell you that it starts from rest and you drop it. Okay, so you drop it given the acceleration due to gravity, the initial velocity, let us say it's 0, and I give you the time, I tell you find the final velocity or find out how long will it take to reach the ground. These kind of questions are, you are given the cause. The cause is the ball started at a particular point and it had a particular speed, and the cause is the acceleration due to gravity, and you are asked to find out where will it reach at a particular given time. Okay, so given causes, find effects. Let's see a few more examples. So let's see an example in heat transfer, let's say. So if I give you the conductivity, so let's say I have a slab, I have a composite slab, I have a whole bunch of conductivities, K1, K2, you would have done all these problems within your heat transfer course. So suppose I give you a series of conductivities and I give you some boundary conditions also. I tell you left temperature is so much, right temperature is so much, or convection is so much on the right hand, etc. You would have done these sorts of problems multiple times. The question is, given the conductivity, find the temperature profile. Okay, can you find out what this is? So what is the cause here? The cause here is whatever material property exists, cause here is energy conservation, cause here is the boundary conditions, and you are asked to find out the effect, which is the temperature profile. Okay. Very briefly, very soon in the next slide you will start seeing the inverse problem of this, but I would also like you to think about what the possible inverse problems could be as I am going over the direct problem. Okay. Now if we look at the medical domain or a simple domain, let's say you have somebody like a trainee doctor, okay, and he would be asked stuff like, okay, suppose a patient has TB, what would be the resulting symptoms? So that person could say something like, okay, there will be weight loss, there will be cough, there will be fever, etc., etc. So given the disease, find what the effect on the patient body is. So that would be an example of a direct problem, a forward problem. Okay, these are typically what are known as analysis problems. Okay, within engineering drawing, you could have something like given an object, find out its front view, top view, side view, etc., etc. So given an object, find its projection. Given a body, given the light, find out what the shadow will look like. These are again forward problems. So please keep on noticing some common characteristics between these problems. Okay. So again, given this kind of body, find out how much, what will project onto a screen. Okay. Again, suppose I give you your house which you are living in and ask you to find out the net floor area. That's an easy problem. Okay, that's a direct problem. You just go measure it, you will get the house area. Suppose I tell you that there is a beginning software engineer in XYZ company, what is their salary? You will at least get a range of salary. So usually a single cause will typically have a single effect or a narrow range at worst, like with the salary. Okay. These problems are very typically forward problems, and these are also called well posed problems. Okay. What well posed means, I will cover a little bit later this week, but we will call them well posed problems. You can already intuitively feel this, what this well posed problem means. It has an answer, and that answer is somewhat a little bit more definite than what I will show you shortly now as a ill posed problem. So these are the characteristics of direct problems. As I said, that's what typically happens within the normal school kind of problems or normal science and engineering problems that we deal with within the academic setting typically. Now, as against forward problems, we have inverse problems, and it's best to see inverse problems in the context of forward problems. Okay, so now let's look at the same problems that we did in the last slide, and now look at what their corresponding inverses would be. Now, as it turns out, most interesting problems both in life as well as in science engineering are inverse problems, and these represent the most practical problems that we can think of. So, here it is in the opposite direction. Here it goes from effects to cause. If I know the effect, can you find out the cause? So, for example, for thousands of years, people had been observing that balls or objects left in free fall, but what is the cause? Okay, so people had all sorts of hypotheses, okay, till Newton came and sort of formalized it. So, what Newton did in some sense was also a sort of inverse problem. So, you can think of this like I am observing a ball and it's falling through air, okay, it's falling through air, you drop it through air and it reaches a particular point. So, you are given the initial velocity, you are given the final time, perhaps you can even measure the final velocity or the distance that it travelled. Now, question is, can you find out g? Can you find out the acceleration due to gravity? Now, it might look like an obvious problem, but please think about this in the realistic practical sense. Now, when it was Galileo or Aristotle or people within India, so you have like all these historical examples, nobody knew that you have to now subtract out air resistance. Air resistance is a real problem that adds noise to this problem. They do not know whether in fact up until Galileo people thought that if you put larger objects they would fall faster, which is not true. If you look at Newtonian mechanics, that is simply not true. Okay, so if I put a larger object also, it is going to fall at the same speed as a smaller object. Okay, so that is confusion that caused by the air resistance issue. So that is why inverse problems are many times a little bit harder to solve. Okay, so now the question is, given these things, can you find out g? So now let's look at the same problems we did in the last slide and go over those examples again. So now the same problem, now I give you the opposite situation. When I said given temperatures, it is important to notice, and I will come back to this point, I have not given the whole temperature, I have given you some measurements or observations of the temperature. This is also a subtle difference, again we will come back to this later on in the course. So when I tell you temperature, typically I have let us say some 10 thermocouples within this slab and I start measuring the temperature. Now notice that when you put a thermocouple, there will be some noise, there will be some errors. So we should account for that too. It will not fall perfectly within a straight line, okay, that is not going to happen because measurements have errors, okay, in them, or measurements have some accuracy requirements built into them. So now we ask the opposite question. We ask, if I give you temperature measurements, can you find out the conductivity of the material, or in this case, can you find out the fact that there are multiple conductivities going on here, and can you find out all of these out? Can you find all of these out? Okay. So incidentally, typically the forward problems that you solve, again if you have done heat transfer, if you have done forward problems in heat transfer, typically you will be given K. K is 10 watt per meter Kelvin, etc., etc. Now the question that you are given is, given the material constant, find out the temperature, but in practice often the harder problem is finding out K of a material. Okay, when a new material is given, you want to find out its conductivity. How do people do it? They do it by making temperature measurements, putting in some theory and then extracting this information out. So literally the way people find out K is through solving proper inverse problems. Okay. Again, the realistic problem that a doctor faces is not a patient calling and say, I have TB, what symptoms will I observe? That even the patient knows. The patient usually comes with a symptom and asks the doctor for the disease. Okay, so that's usually the direction in which we go. Only then can we actually cure it. So typically symptom could be, doctor, I am having cough, I am having fever. Then the doctor could say maybe COVID, maybe TB, maybe something else. Notice the fact that your options actually multiply here, unlike the forward problem. The forward problem is usually somewhat like a convergent problem, the inverse problem is somewhat like a divergent problem. So here you could have multiple diseases which correspond to the given symptoms. Again notice we are only making some finite measurements. Okay, so you might measure temperature, you might measure the frequency at which a person coughs, you might measure the weight loss of this person, you might do an RT-PCR test. So all these measurements, based on that, based on measurement, you want to find out the cause. Okay, so that is what is again typical of an inverse problem. Again, if we go to the engineering drawing problem, we give the projection or we give multiple projections. You might have, in case anyone has done engineering drawing, you might have done this, find out the object. This typically happens within CT scans also. We will come back to that later on this week. I will just briefly discuss that because they are an important application of inverse problems. But here the same thing, here suppose I give you just this, that this is the projection, can you guess the object? Now you can see that it does not necessarily have to look like only this object. You need at least a few more projections for you to start guessing at what the object really is. So this is again typical of an inverse problem. Again, suppose I give you that you have a 1500 square feet house if you are lucky, and you want to find out a design, a floor plan for the house which satisfies certain constraints. That is a design problem. So design problems typically also are inverse problems. Finally, you might know the salary range you are shooting for, but you might have preferences. You want to know which job will satisfy this and satisfy some other constraints, like you want to live in the city, etc., etc. These are all inverse problems. Obviously, all the techniques we are going to do are not going to help you find a job or something of that sort. Okay, what they are supposed to do is, my point here is inverse techniques are more general than just things applicable to heat transfer. It is mathematically a robust subject which applies itself to multiple fields. I will come back to that. You will have very, very surprising applications, as I will show in later on this week itself. Okay. So what is characteristic of inverse problems is there could be multiple causes that correspond to a given effect. So these problems are known as ill-posed problems. So remember, well-posed problems, forward problems, ill-posed problems are typically what are known as, or that is what typically makes inverse problems harder. Otherwise, inverse problems are just like forward problems, you just solve in the opposite direction. Okay, but ill-posed problems is, if typically an inverse problem is ill-posed, it makes the solution of an inverse problem a little bit difficult. So just to summarize, what is an inverse problem? Okay, so typically direct problems or analysis problems are what we usually do, they are forward problems. A forward problem goes from cause to effect. I will show you another characteristic of it shortly, but inverse problems go in the opposite direction. Given the effect, find the cause. Now notice it seems like the same effect has multiple causes. This is possible, just like the projection case, or usually what tends to happen more often, like I said, that these are divergent, that nearby effects, okay, can actually have very, very far away causes. For example, two people could go to a doctor with very, very similar symptoms. I in fact read a horrifying case very recently, like last week, of a lady who had gone to the doctor with just some running nose. It turned out that she had some damage in her brain, some cerebrospinal fluid was leaking out, and the doctor, the doctor figured it out based on some small indication. I think maybe she had a mild headache or something of that sort. She thought she had an allergy, but it turned out, so you can have effect which is just some symptom of a cold, but it could be something as far away as allergy versus brain damage. Okay. So this is a dramatic example of an inverse problem where just small changes in the effect, just some mild changes, which is why we go to medical professionals, because they can figure out these subtle signs. If they are good, they can figure out these subtle signs that could be like vastly different causes for the same thing. It could be harmless or it could be very, very harmful. Same thing happens within the engineering domain too. The numbers can be vastly different based on a small measurement change at one place. This is what is known as the stability problem, which I will come to once again later on in this week. Okay, so we go in this direction. from effects to causes. Okay. So, just to give you sort of a overall definition of what we have looked at over the last couple of slides, it is that the inverse method or inverse method is a process of calculating from a set of observations. So, please notice this word, from a set of observations. So, the set of observations could be thermocouples which you have kept, or the doctor could be making some measurements on your body, or you could be taking some projections of the object, etc. So, these are all measurements or observations. From that you want to find out the causal factors. Causal factors basically simply means causes or numerical causes that produced them. Them here means the observations. So, you are observing and you want to find out what possibly could have led to these observations. So, that would be a definition of what an inverse problem is. Okay. So, let us now look at a few examples, concrete examples. I gave you sort of toy examples. I want to give you more realistic examples, and then I will show you some historic examples also in the next slide. Okay. So, here are some examples of forward versus inverse problems in various fields. Okay. So, remember what inverse problems are or inverse methods are. You want to infer the causal factors from a set of observations. So, please keep this at the back of your mind as we go further. Okay. So, let us look at some forward problems versus their corresponding inverse problem. So, here is a famous problem. This is called finding out the shape of a drum by hearing it. Okay. So, for example, a forward problem, well defined problem in acoustics, in case you have done this, is suppose I give you the shape of the diaphragm, suppose I say it is circular, okay, and I give you properties also, okay, just like conductivity in thermal, you have to give the properties, the elastic properties of this diaphragm, and you want to find out what sound will it make if I hit it. That is a forward problem. Given the shape of the drum, find out the sound that it will make. What is the inverse problem? The inverse problem is, from the sound, you are only hearing the sound. Can you find out what the drum itself looks like? Okay, so this looks like an impossible problem, and in fact there was a very famous article very recently about this, recently meaning about 20-30 years ago. Mathematicians showed that this is actually not a well defined problem. For the same sound you can have different sort of shapes, but you can get remarkably close to the original shape just by listening to the sound. So, that sort of analysis is possible. Okay. Now, here is another example. I will spend a little bit more time on this in the next slide because it is of historical importance in inverse methods. Is if you know its current location, this is very much like the ball problem with Newtonian mechanics. Given current location, can you find out future location, okay, based on orbital mechanics. Now, the inverse problem is you are given some neighboring orbits and you want to find out a missing planet. Okay, I will show you that this actually happened historically. So, that would be an example of an inverse problem. Again, I will skip this for now, we will discuss this in greater detail in the next slide. But here is a more interesting problem. So, suppose I give you a language, I say Tamil and say Happy New Year or New Year wishes, New Year greetings to you. So, in Tamil you would say Puttandu Vaalthugal. Okay. So, that would be a forward problem. Given a language, find a sentence, okay, find an equivalent translation sentence. Even though there are multiple ways of translating, as I said, the range is narrow. Now, here is an inverse problem. The inverse problem is, and this is what Google has done here incidentally, Google Translate has done this. I just wrote this word called Puttandu Vaalthugal, and you notice this word, it says detected, okay. It found out the language. So, whenever from the language you want to find out what language it is, that is a detection problem, language detection problem. That is an inverse problem. Given the language, find out what it is. Okay, so that is the cause. The cause of the sentence is the original language. Now, surprisingly enough, it might seem like these three are very different problems. Okay, how is language in any way, shape or form connected to the sound of a drum or the motion of a planet? Let us come to one more example. Again, I will let me spend some time here. So, when you go for a CT scan, okay, so what happens is, like you have these detectors, and you know you have essentially, mathematically speaking, multiple projections of your body being thrown off and being detected by multiple detectors. Okay, so this is what we would call a CT scan. So there are multiple 2D projections. Okay, now if you want CT reconstruction, you want to find out the 3D body that corresponds to all these 2D projections. Okay, so that is what is a CT reconstruction problem. Okay, now if you look at it, very diverse fields, from acoustics to orbital mechanics to natural, what is known as natural language processing, this is known as NLP, natural language processing, to CT reconstruction, to biomedical applications. As it turns out, all of them use the same mathematical techniques. This is where the power of mathematics lies, in unifying. If many of you would have done some courses in solid mechanics, some courses in fluid mechanics, some courses in heat transfer. If you notice, many of the differential equations will be the same. Now, as far as the process is concerned, okay, so the stretching of a bar is entirely different from what happens in really viscous fluid, is different from what happens within a slab, but the equations will look very similar. In fact, they are identical, except you might want to switch T for velocity or temperature for velocity or something else. Now here is the point, mathematics unifies these seemingly completely different applications. Now notice again, I will tell you, there is nothing more different than having a biomedical application than, let's say, language speaking, but nonetheless it is identical. The mathematical techniques that we use to detect a language will turn out to be very similar. Okay, at least the sequence of series of techniques which we will cover within this course are capable of handling both. When we come towards the end of the course, I will discuss how something like language detection could happen even using exactly the kind of inverse techniques that we have used for heat transfer. So that's in some sense the exciting part, the part that all of these subjects come together, and that's really what we are also seeing in the modern machine learning revolution, because all of it is essentially a subset of inverse techniques. Okay, so my point of showing these diverse examples is not just to show you examples, but to tell you that there are the mathematics which unites all these fields, and that's why we will also be covering some of mathematical techniques. The course is a mathematical course, incidentally, so it's a numerical course, it's also a mathematical course because it's mathematics that unites these diverse applications. Okay, I had talked earlier about well-posed and ill-posed problems, so let me just show you some formal definition of what these are. I had casually introduced you these. So these categorization of what constitutes a well-posed problem was first given by this person called Hadamard, a scientist called Hadamard in 1923. He gave the following criteria for what constitutes a well-posed problem. First is, when you give a problem, there should be a solution that exists. Okay, so you cannot give a problem for which there is no solution at all. So an example of a bad problem or an ill-posed, you can't really call it an ill-posed problem, but you can call it a not a well-posed problem, is suppose I say solve x square equal to -1 where x is real. Okay, this is, technically speaking, mathematicians will frown at this kind of example for me saying that this is not a well-posed problem. But anyway, I mean, it's not a proper problem because the solution doesn't exist at all, okay, within a real number. So a well-posed problem must have a solution that exists. Okay, so you must give adequate boundary conditions. For example, if I give you only one boundary condition, then it's not really a well-posed problem. Okay, let's say I have a slab, I give you one side, I don't give you the other side, you can't really find out the temperature distribution. Second thing is, the solution must be unique. Okay, so given a certain set of boundary conditions and a particular thermal conductivity, and given that it's steady state, etc., you know that there is only one possible temperature profile possible. So the solution is unique, means it's a well-posed problem. Third and a very important criteria, and this is where inverse problems typically run into trouble, is stability. Okay, so the idea is this: if you make small changes to the input data could be, let's say again in the slab example, this could be some small perturbation to the left temperature, some small perturbation to the right temperature, some small perturbation to the conductivity. If you do that, you don't expect that the temperature profile will suddenly jump to something else. Okay. So, you expect that small changes in input will cause small changes in output. Okay. So, that is small changes in the cause small changes in effect. We are not accounting for turbulence etc., but other than that typically looking at a well posed problem means small changes here lead to small changes in the output, and that is what is defined as a well posed problem. There are more technical requirements here, but I will not get into those, but this is just to give you a little bit more detail about why we call inverse problems ill posed. So, when we look at a forward or a direct problem, these are usually well posed problems. Typically these are well posed problems. Inverse problems, existence usually is true. I mean, there is a temperature profile. If I give you some thermocouple measurements and I ask you what is the temperature profile, you know that something does exist there. Uniqueness means you have to be a little bit careful. How do you ensure? We will do this later on in the course. Most important is stability. Like I said with the doctor example, in case just one small change is made to the symptoms, it can lead to a large change in what the possible diseases could be. So, stability is a real difficulty with inverse problems. So, please remember this, inverse problems are typically ill posed problems. Usually, I mean not all inverse problems, but usually ill posed problems, and primarily because there are stability issues. And what we tend to do is we use a technique called regularization in order to reduce this ill posedness and to increase stability. Okay. So, to reduce ill posedness of the solution, we use a technique called regularization. Okay. So, we will see that later on in the course. So, let us now come to a brief history of what inverse problems are. So, really speaking, the formal history of inverse problems starts somewhere here. Okay. So, somewhere near 1970 is where you can say is the cutoff of really calling something an inverse problem. I do not know the precise history, it might be in 1960s too, but somewhere here is the cutoff point, somewhere here 1970. But before that, people have been solving inverse problems implicitly. Like I said, most interesting problems, even if you can call a design problem an inverse problem. But within science, the use of some proper techniques to get here starts with Gauss, or even with the first example that I have shown here. Not a collaborative effort of these four, but historically there were 4 people involved in this beautiful discovery, a sort of dream discovery of Neptune through the observations of the orbit of Uranus. So, what happened was the observations that people were making about how Uranus's orbit was moving were different from what Newton's laws of gravitation would have predicted. Okay, so this is what, or Kepler's law of motion, whichever way you want to see it, would have predicted. So, both these guys, Bouvard and Adams, independently speculated that the reason why this is not quite matching might be because there is an extra planet. Okay. So, that there is a planet after Uranus that is causing these perturbations, and if we account for gravitational effects of that, we will be able to see that this accounts for Uranus. So, if I remember right, it is Verrier who did the calculations and said something like, okay, if what we have speculated is right and that there is an extra planet somewhere here, now observing Uranus, so now notice this, make a set of observations and make a guess about the causal factor. So, notice this, you made a set of observations about Uranus, you have a theory. So, typically the typical mixes are, you have observations, you have a theory, and based on these you guess at a cause. You try to in fact give a numerical cause as much as possible. Okay. So, your observations are, in the language example, the observation would be 2 words, Puttandu Azhuthugal. Okay. You have a theory that each language works a particular way. I will show you how machines do it maybe later on in the course, but you actually try to guess at the cause. Oh, the cause is the person must be speaking Tamil, that is why he made those strange noises. Similarly here, The observations were observations of the orbit of Uranus. They had a theory. The theory here was Newton's theory of gravitation. They said, okay, we can account for this if I add an extra planet. Remarkably enough, Verrier did the calculations and said, okay, if the calculations, if these calculations and this theory is correct, we should find Neptune approximately here. And this person did the observation, and magically enough, they found it almost exactly where the theory predicted. So, this is a remarkable success of the scientific method, of Newton's law of gravitation, etc., etc. Of course, there is a counter example when Mercury's motion was not orbital motion, but what is called as a precession of the perihelion of Mercury. Once that was there, so people made the same thing, like maybe there is like another twin planet somewhere there, and they did that. That calculation completely went off. People did not observe any new planet, and it took Einstein the theory of general relativity in order to show that that accounts for the extra motion of Mercury. So, it is possible that your theory is right and your observations are right, then your cause would be right, but sometimes it is possible that your theory itself could be wrong and you have to modify your theory. Okay, so that we are obviously not going to deal with within this, though I will touch upon this when we come at the end to neural networks. Okay, so but it could be either possibility. So, historically this neat problem, okay, even though it is not, if you look at discussions of history of inverse problems, you will find this, but it is a good example of how it could have gone both ways, okay, with Mercury and Neptune. One to the confirmation of the theory and an actual observation of the causal factor, and one which shows the theory itself had to be modified. Now, proceeding further, the first real mathematical attempt at a strong inverse problem was by Weyl, Hermann Weyl. This is a mathematician, 1911. I showed you the example of a drum. So, the problem that he solved was very related to that. So, this title I have given here, Can We Hear the Shape of a Drum, came later in the 1960s or 70s. It's a popular article, I think in the American Mathematical Society or Physical Society, I forget which publication this was in, but it is the same problem that I showed you. So, he solved the mathematical equivalent of this problem. In some sense you can say that the first strong application of inverse kind of techniques here. Then in 1929, I think this was Victor Ambatsumian, I am not sure I am pronouncing the name right. 1929, there is an application in a mixture of astrophysics, atomic structure, etc. Now, look at this problem. You might not understand it in the version given here, but you can think of it as a version of, if I give you the matrix, can you find out its eigenvalues? That would be a forward problem. But if I give you a set of eigenvalues, can you find out the matrix which will cause it? You can see automatically that there could be multiple matrices. So, how to solve it in a physical setting, like I said, in an atomic structure or a vibrating string stretching, was something that Victor Ambatsumian did, I think as part of his thesis, maybe, I am not sure, I do not remember perfectly well. So, 1970s, like I said, roughly is where you can start seeing this approach being formalized. So, Gelfand and Levitan, both Russian scientists, started solving the inverse scattering problem. Scattering problem is something that occurs for light, occurs in general with radiation, so it has connection with heat transfer also. So, these people used a series of techniques. We will not be getting into those techniques, we are going to look at some simpler techniques within this course. Now, within our field meaning the field of this course, one of the first people, or probably the first person, was Professor George Beck, 1980s. There is a famous couple of books by him too in inverse heat transfer. He was commissioned, I think, by NASA to solve, I will show you this example shortly, solve the re-entry problem, like a vehicle is re-entering the atmosphere and they want to make measurements on the vehicle, but they are not able to do it because of the high heat transfer there. So, they had to solve an inverse conduction problem there, and that in some sense is the first formal application, and I think probably because of its space application far more than 1970s by Gelfand and Levitan, you can in some sense also think of this as the time that inverse problem suddenly exploded. Okay, so, after that there have been a huge number of applications in mathematicians who are interested in the theory, physicists, of course, in a large number of fields. I have already talked a few here: acoustics, atomic structure, then geophysics, finding out the constituents of a planet based on measurements that you are making from on the surface, etc., etc. Then imaging, like I showed you, CT scan, etc. Natural language processing is the example I showed you of Tamil. Machine learning, again these two I will cover at least a little bit of this later on in the course, and then of course the reason why we are doing this course in heat transfer. Okay, so a large number of applications in all these problems, and that's a brief introduction of the history of how inverse problems developed. Now, having looked at how inverse problems developed across various fields, let us look at some possible applications of heat transfer, inverse heat transfer. I will show you the broad applications in this slide, and I will show you one specific application, in fact historically the first application, in the next slide. So, you want to estimate, so that is a key word, we are estimating. Why are we estimating? We are not directly calculating because we already know the solution is non-unique. So, when the solution is non-unique, you are only going to estimate. Okay. So, non-numerically you are going to guesstimate without any kind of stuff, but you can actually give some estimate with some error bounds. That is what we would like to do. So, estimation of thermophysical properties of a material like conductivity, etc., etc. So, that you can try to do, as I talked earlier. In fact, a straightforward important industrial use of inverse methods is there. You want to find out the boundary heat flux in forced convection. That is an example of how do you find out the heat flux given all the other details. You want to find out spatially varying heat transfer coefficients, okay, in different geometries. That is an example of inverse heat transfer. If you want contact conductance, sometimes it is very hard to directly measure this in a conjugate heat transfer problem. That is an example of inverse heat transfer. Now, of course, you can look at radiation also. So, you want to find out bulk radiation properties, you want to find out emissivity, etc., etc., and in various kind of environments. All these are examples of inverse heat transfer problems. We will primarily be looking at toy problems within this course. That is just to, there is a reason why we just did not call it inverse problems in heat transfer, but inverse methods in heat transfer, because the emphasis here is going to be on methods, so that you can apply it across different fields and not just heat transfer. But the context is heat transfer, otherwise it becomes too difficult for people to sort of pin down what they wish to do. Okay, here is an example of an inverse technique applied to a heat transfer problem. As I said, the historically first example we have of such a thing. So, this was by Professor Beck, George Beck, and he was, like I said, I think this was NASA which called him to figure this out. So, here is the problem. You have a atmospheric re-entry vehicle. Some of you would have seen this kind of shape. I am not sure if the movie Martian shows that, but I think the movie Mangalyaan, if any of you have seen this Hindi movie, it shows what happens when you enter into the atmosphere. You will have this typical blunt body shape. This is a high Mach number. Okay. So, typically 3, 4, 5, 6. So, typically there will be this what is known as a bow shock up front, and because of that there will be huge heat transfer here. As you can imagine, something is coming back rapidly into the atmosphere, that is why it is a re-entry problem. Now, all this ablates. Okay, so, this material here, it is kept as protective material to protect whatever components exist here. So, it rapidly sort of decays, and you want to find out whether it will be able to take the heat transfer load. Okay, so, you want to also make live measurements of this. So, suppose I zoom in on this portion, what you will typically see is something of this sort. So, what you want to measure is this, we want this. It is not a single number, notice this is q of t, which means t is time. You want heat transfer as a function of time, okay, at the surface. So, this is the surface here. Now, they want to measure this, let us say NASA wanted to measure this. Now, the point is you can't keep a thermocouple here, obviously not, okay, you can't keep it there, it is just going to, I mean the heat transfer load is just too high, nothing is going to, no material is going to withstand that. So, what you do is you bury it within. okay, you keep it somewhere inside. So now here you have this interesting inverse problem. Why is it an inverse problem? The forward problem is like this. Suppose I give you Q of T, can you find out how the temperature varies with time? That is a straightforward problem. These are known boundary conditions on the other end. It is more or less like a slab, at least if we want to model it simply. Here is a slab, one end I know the boundary condition, I know the heat flux, other end I know the boundary condition, let us say it is either heat flux or the temperature, and find out a temperature at a point in the middle. That would be the forward problem. But here we want the inverse problem. What is the problem that we want? What we have measured, here is the set of observations. At various times you make measurements. So you keep on making measurements at here, and this, since it is buried within, it is not going to burn away. So it makes good reliable measurements, let us say approximately reliable measurements, and it tells you, okay, here is my time history of temperature. Can you please tell me what would be the heat flux at these corresponding regions? So this was the problem, as Professor Beck talks about in his book, which I have written here, which is where I got the pictures from. This book is called Inverse Heat Conduction, written in, as you can see, 1985. It is called Inverse Heat Conduction Ill-Post Problems. Okay, so these ill-post problems are because there is no unique Q which corresponds to this temperature. So how do you find out what actually happens in practice is the interesting problem. So you can see here, this is the output. Even though this is the cause and this is the effect, the cause is the heat flux which is being generated due to the re-entry vehicle entering rapidly into the atmosphere, and the effect is the temperature. By looking at the temperature, we want to find out what the cause was. Okay, so it's like the sun heats us. Based on whatever we are getting, we want to guess various things about the sun. What's its temperature? What is its composition? Again, that would be a inverse problem. Typically in a heat transfer course, you will be doing the other way around. Okay, given the emissivity, etc., find out the temperature on the earth. You want to do exactly the opposite. You want to guess at the opposite thing. Okay, so this is an example, or historically first example of inverse problems being applied in heat transfer. And like I said, after this, the entire field of both inverse heat transfer and inverse methods in other places took off, including CT scans, etc. Within inverse problems, whether it is in heat transfer or in other fields, there are two types of problems. This is called a function estimation problem versus a parameter estimation problem. Okay. So a parameter estimation problem is you want to estimate the conductivity from the temperature or the heat flux. So a parameter estimation problem is finding out one property or one number or a couple of numbers. Okay, it's a limited number of numbers. This is in some sense a discrete problem. So like I said, one or two things that you wish to find out. It could be a few things also. Like I said, if there is a slab with multiple multiple different materials, it could be K1, K2, K3, K4. That's a parameter estimation problem. It's an easy problem. The function estimation problem is a harder problem. It's sort of the problem that I showed you in the last slide when I showed you the atmospheric re-entry problem. So the function estimation problem is find an entire function. Okay, so it could be, like I have said, the entire temperature distribution within a slab, okay, from other information. Okay, so that could be one such example. Another such example is like we did, find out temperature as a function of, or Q as a function of time. So this is an entire function you are trying to find out, not only at one or two points or two or three parameters, but an entire function is what you are trying to estimate. This typically involves usually what's known as solving an adjoint problem. Okay, so I might or might not cover this, but I will give you a brief idea about how to do this towards the end of the course when we looked at advanced techniques. So primarily within this course, this is what we will be concentrating on, parameter estimation. So I want to point that out. More advanced courses will also cover function estimation, but this is, since it's being taught primarily at an undergraduate level, and parameter estimation itself has very interesting applications and interesting techniques. That's what we'll primarily look at. As I have mentioned here, function estimation will be looked at towards the end of the course, probably the last week. So here is a summary of what we have seen so far about inverse problems. Many important practical problems are inverse problems. An inverse problem is something which says given the effects find the cause, or given a set of observations find out the causal factor. Within this course, this causal factor will often be a numerical causal factor. There is actually a number associated with it rather than something like a disease, but I will come back to this later. Okay, they have the following characteristics. They are usually ill-posed. Remember, ill-posed means that it will be non-unique or it could be unstable. Okay. These involve estimation. As I said, you can't just calculate it, you actually have to estimate within the certain region or a range, as we will see within the probability and statistics things. They can be either of the parameter estimation type or the function estimation type. So numerically, that is what we are trying to estimate. Okay, we are trying to estimate the parameter or we are trying to estimate the function. So thank you. In the next slides, we will start looking at why, what the general procedure of solving an inverse problem is. Again, I will do it primarily non-technically, and why we involve forward problems while trying to solve the inverse problem. Thank you.